Okay, we're going to talk about measurement reliability today. And you can obviously see that that's the title of our presentation. This really translates into two new terms, okay? The first term is going to be accuracy. Could you guys go ahead and shut the door, please? Okay, the thing about accuracy, okay, is when you're a scientist and you're looking at a bunch of data, oftentimes it's data that you're comparing to things that we know. So for instance, if you're testing a concrete sample for a roadbed, you probably have a series of numbers that you could say, hey, these are good numbers to have. And so you would compare your test material to numbers that you know are acceptable. And if the concrete doesn't work, then you have to tear it out of the ground and do it over. If concrete is acceptable, then you can leave it in the ground and use it for the roadbed. See, so we would say that in order to be accurate, in order for something to be accurate, it has to be close to what is called an acceptable value, okay, or what we call a true correct value. So on this, if you're taking notes, a true correct value is also known as an accepted value. Something that's been tried again and again and again. That's honestly lagging a little bit here. Like so. All right. Looks like it's paused here. Hang on one second. Okay, let's see if this one works. However, precision is something that's different. Okay? Precision is something that scientists, regardless if they're looking for accurate data, have to worry about. Every device that we use to measure, thermometers, meter sticks, something called caliper, which measures even smaller than meter sticks. Okay? All of these devices measure numbers that have decimal places. Okay? So sometimes if I'm looking at 1 meter, that might be 1.0 meter. If I'm looking at something that's in millimeters, I'm going to go, so for instance, I want to deal with 33 millimeters. I'm going to go 0.033 is 33 millimeters. Okay, and we're going to look more at those numbers later on, but hopefully you can get the gist that the smaller the number, okay, the more decimal places that number has, or the smaller the unit. So millimeters are really small, so it goes a few places past the decimal. Nanometers are really, 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 really small, so it goes a lot of places, 9 places past the decimal, okay? Why do you think this is important for scientists to have the right instruments to produce the right precise values? Why do you think this is important? Anyone want to give me, why do you think it's important? Is there anything that you use on a daily basis that could be life-threatening if it's not made well? Yeah.
A car.
A car, sure. Did you know that when they make all of the components for the engine of a car, or even the brakes, or the rims, or the tires, or the aerodynamics of the car, okay, every piece of that car is made with the utmost precision, which means that they're not just eyeballing it. They have to use instrumentation. Sometimes they have to use lasers because our eyes can't even process the fine details that are needed to make those pieces of that car. Okay, so they have to use computers. They have to use fine machines and instrumentation. They have to use very precise equipment. Okay, worst case scenario, the engine blows apart if you don't use the right equipment or the right precision. So that's very important for the people that make that car. If you're somebody who doesn't pay special attention to precision, you'll lose your job. Okay? You'll lose your job. Some companies like NASA, they have to get down to so precise numbers that are so precise that Even some computers can't handle those numbers. Okay? So, because they can't let a single atom of air escape something that's going into space, the space station, etc. If one atom of air gets out and then more atoms of air get out, it could mean the end of human life. So we're talking about precision is not something that I'm just making you learn. It's something that affects your day-to-day life. There are people, maybe you someday, that have to be very precise in the things you do. For instance, if you have 1 milligram more of medicine, if you're a pharmacist, that could cause somebody to die because it could be an overdose. So your job relies on your ability to measure and be precise. Some of you will have jobs like that. Some of you will be pharmacists. Some of you will be nurses' aides. Some of you might be physician assistants. Some of you might work as engineers. Some of you might work as computer techs. All of these things rely on precise measurement. So this is important. Okay, so precision, if you have not written it down, precision is how closely a set of measurements are to each other, and it relates to the decimal place of a number. Okay, so there's really two things that we take into consideration here. The more decimal places a number has, the more precise it is. It also tells us whether or not we can use a certain piece of equipment. If a scientist is taking measurements of a piece of material, and there's 5 or 6 places past the decimal in that scientist's measurements, there's no way you could use a meter stick to replicate that scientist's results, because meter sticks only go to 3 or 4 places past the decimal. That's the most precise a meter stick is. So if, like I said, if the numbers have 5 or 6 places past the decimal, a meter stick is not what they use to measure. They probably use something like a caliper or a laser or something like that. Calipers, by the way, are tiny little things that look like pliers, but they measure very, 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 very small increments. Okay? Sometimes we use them to measure the difference, sometimes the difference of 100th or a 10,000th of a millimeter. Okay, so if you take a millimeter and you divide it into 10,000 segments, that's the precision of a caliper, or somewhere right about there. All right, so the question is, in these 3 diagrams, are we dealing with accuracy or precision, both or neither? So in this first diagram, would you say it's accurate, precise, both, or neither? What do you think? Yeah, neither. He's right. First of all, these x's are not close to each other. Precision identifies how closely a set of measurements are to each other. So they're not close. And are they all near the bullseye? No, so they're not accurate, because they'd be right in the middle if they were accurate. So this is neither. What about the next one? Yeah. It's precise, but accurate? Not accurate. What about the last one? Caitlin? It's both. They're close together, so it's precise, and it's accurate because they're right at the bullseye. Okay? You will not have a set of numbers that is accurate and not precise, because all the numbers have to be really close together in order to have an accurate answer. All right, I'm going to give you 2 examples similar to 3 questions on your test. Okay, so your test has 3 questions that deal with accuracy and precision. Okay, and this is what they look like. So I'm going to give you a set of data points. There will be no units associated with this. There's just going to be numbers. And there's going to be what is called an accepted value for comparison. Okay, so this is what we have. Let's say that we're dealing with 12.54, 12.53, 12.50, And there's something called a tolerance. Okay, that's how far off these numbers can be. And the tolerance is plus or minus 1.0. Okay, the accepted value is 7.63. Okay, the question you have to ask yourself is my data accurate, precise, both, or neither? There's 4 options. What do you think? Accurate, precise, both, or neither? Chloe? Precise. It is precise. All of the numbers are really close together. They're within my tolerance, right? They're definitely within 1.0 of each other. As a matter of fact, they're within 0.03 of each other. Very, very close data. So they're definitely precise. Okay? What about accurate? Are they more than 1 off from the accepted value? 12.54, 12.53, and 12.50. Okay. And the accepted value is 7.63. So are they more than 1 off from the accepted value? Yeah, they're about 5 off from the accepted value. So they're outside my tolerance range. So therefore, they are not accurate. They're precise, they're close together, but they're not accurate. Any questions about this? What if my tolerance had been plus or minus 10? How would that change the outcome? Yeah. They'd be both precise and accurate, because not only would the numbers be close together, but they'd be within my tolerance. Since the accepted value is only 5 off and not 10, that would be what we would consider close, and so they would be precise and accurate. Okay? What if I changed my tolerance to 0.0003? Okay, so they had to be super close. They had to be close down to 5 places past the decimal. How would that change my answer? Erica? They'd be neither precise nor accurate. Okay, first of all, the data doesn't even go 5 places past the decimal, so it wouldn't be precise enough. And they could only be 0.00003 off, and they're almost a million times more than that. So definitely neither. Okay. Now, we'll put this back the way it was. It was plus or minus 1.0. Let's look at another example here, different data. One 1.76, 1.72, 1.79. Okay, that's my data. My tolerance, so how far off they can be, is plus or minus 0.10. Okay, and the accepted value is 0. Or no, sorry, not 0. I apologize. 1.80. Okay, you're going to have to look at these numbers very closely. Okay, the data is there. When I'm looking at data and I have to relate it to tolerance, okay, what I do is I find the largest number and the smallest number, and I find out how far apart they are. So what is my largest number? Colby? 1.79. And what's my smallest number? Hannah? 1.72. So if I subtract 1.72 from 1.79, what's the difference there? What number does that? Yeah. Yes. 0.07. That's my, what we call, it's a differential, or that's how far apart my data is. Does that fall inside my tolerance? It does. So we can say that the data is precise. Absolutely. Okay, definitely precise. So that's good. Okay, now we find, hang on one second, Alina. We find the number that's farthest away from the accepted value, and we do the same kind of thing to see if it falls inside our tolerance. So, Mr. Hogel, looking at this information, the accepted value is 1.8. What number, which of the three numbers is farthest away from 1.8? Yeah, 1.72. Okay, does anyone want to say how far away is that? Hannah? 0.08, very good. Okay, so our accepted value is, nice job, 0.08. Does that fall inside our tolerance? What do you think, burglar? Yeah, it does. It's definitely less than 0.1. So that would mean that this is also accurate information. Accurate, 1C or 2? 2?